Hello everybody, welcome to a new video with me. In this video we're going to discuss something called rhodiation. Now if you look closely, this word rhodiation, it personally doesn't have any meaning, but it is consisted of two words, rho and radiation, with their own meanings. And we see that in physics, rho is often used as the density, and radiation, it's a way that energy is uh, given throughout the universe. Therefore, this is basically about how the density of energy changes. And what does it change to? We see in the bottom line here that it also changes through time. First off, we know that the universe is expanding. It's visible on large spectrum, on large scales. You can see further galaxies moving away from us. That's not because they're moving away because their internal velocity. That's because the universe, or as we can say it as, space in the universe is expanding and bringing things away from each other. Those things in space, they also include photons. Uh, the photons, and we know that photons are things that emit radiation as a way to emit energy. This expansion stretches out the photons or makes them more red, or what we call redshift. You can see the diagram right here. So we see that the number of photons doesn't change, but because the universe is expanding, the wavelength of the photons, they increase, and we know that as redshift. Uh, how do we mathematically model this expansion? With this redshift, or the z, or as we know, the change in the wavelength of a photon divided by its original wavelength. And after doing the algebra, we can see that the wavelength after, when compared to the wavelength before, is equal to z plus 1. Right? Now we apply Wien's law, that the temperature is inversely proportional to the wavelength of the photons. So because the photons are getting bigger, the wavelength of the photons are getting bigger, that means that they emit radiation at a temperature that is lower. Okay, we see this. The temperature is decreasing, such that when we compare the photon after redshifted to the one before, it should equal to the temperature, the real temperature, and the temperature that we sense it to be right now. Notice that in astronomy, the T accent, or the temperature after the redshift, we consider it as T0 because it's measured at T is equal to 0, which is right now, and the T nil, or the temperature of the original object, is T at a certain time, or TT. It's an odd way. And another way you can model it, if you know the type of universe and how the universe expands through time, you can also model it as T nil is equal to Tz, but we don't really know. It's actually based on the case, whether it's matter dominated or radiation dominated, or dark energy dominated. Now we also know that based on the Stefan-Boltzmann law for black body universe, of course, we try to keep it ideal so that we can understand what's going on, is that the energy of the radiation is proportional to the temperature to the power of 4. Alright, so we see that the energy is proportional to the temperature to the power of 4, and the ratio between the temperature then and, or T or T nil, divided by the temperature now, or T0 or T accent, is proportional to this z plus 1. So in order to find the ratio between the energy then and the energy now, we just have to do this z plus 1 to the power of 4. So we see that z changes through time, and such because of that, the uh, radiation from the energy also changes through time. Therefore, radiation is a journey through time. Thank you for watching this video. I hope you enjoyed and learned something new, and that's all.